So I guess let's get started. We are 2 minutes past. So welcome back, everyone. Hope you enjoyed the poster session. So next up, we have a plenary talk by Elizabeth Holm. Liz is a professor of material science and engineering at Carnegie Mellon University. Before this, she spent 20 years at Sandia National Labs. She was a computational material scientist, so she's worked on a bunch of different things and has received a lot of honors and awards, including Fellow of ASM International and TMS. She was 2013 president of the Minerals, Metals, and Materials Society, and she has been a member of the National Materials Advisory Board. And I guess today she's going to tell us how to use computer vision to create maybe Google-like image search for material microstructures and other interesting things that you can do with computer vision, maybe mapping structure to properties and so on. So take it away, Liz.
Great. Thank you, Arti. And thank you all for being here at what I know is the end of your long day of conferencing, of workshopping. I'm in the middle of the day. I'm here in California at a different conference, as I was mentioning before we began, and so I appreciate that that you're holding out to the end here. My hope here is to help you understand how material scientists in particular use some of the techniques that you all develop in machine learning and computer vision and so on towards what we do scientifically and in our research and in our engineering applications. And so let me start by setting the stage. And for you, this will be very basic. You know, we know very well by now that with deep learning methods, AI systems are sometimes able to beat humans at various tasks, not the least of which is in analyzing images. And one of the many famous studies along these lines is from the Google group, who trained a computer vision system on chest X-rays, standard chest X-rays, and found that the computer vision system could outperform human radiologists in identifying abnormalities in those chest X-rays, both in finding them and in classifying them. And so that's the kind of thing that makes us think, wow, there's a lot of potential here to use these methods in fields outside of computer science. Now, what are the components of deep learning for image data? We know them well. They're typically convolutional neural networks, which, as you know, involve millions of parameters in their training. And because they're big and deep, they require big data to train them. And so we typically train computer vision systems on big data image databases. ImageNet is one of the many and one of the most popular. And that means typically, since we need to train millions of parameters, we're going to need millions of images as well. Once we do have a trained computer vision system, we can do a lot of useful tasks that start as basic as visual similarity, and they go through the classification, segmentation, object detection, and then the image manipulation tasks like generation, super resolution, and so on. So there's just really a wealth of applications. So that's background that I think we probably all share in common. Let me now take you to my field, which is material science. And in particular, it's microstructural science. So I'm going to give you the 2-slide crash course in microstructure. Okay, bear with me. Look around you in your real environment. There's something that you're looking at. And that something may look like it's uniform, may look like it's just kind of a blob, but it's not probably. If you were to look at the substructure of that material, and we call that substructure the microstructure, that's the structure usually below the visual length scale, but above the atomic length scale, you would find that there's structure there, that there's patterns. And it turns out that that structure governs a lot of the properties of the materials that you deal with. Are they hard or soft? Do they feel cold or warm to the touch? Do they conduct electricity? If so, how well? And so on. And pretty much everything has a microstructure. Here's one example, mayonnaise. Mayonnaise is a suspension of oily droplets. Those are the white spheres in this image in a watery matrix, which is the kind of grayish matrix here. And because oily round things roll easily, mayonnaise spreads easily. So the microstructure, which you don't see with the naked eye, governs the properties of the material that you use. And the same is true for your brain with its dendritic structure of cells making connections, or hailstones, which are formed by an accretion mechanism where they go up in the clouds, get a layer of water, fall down, and do it over and over. And you see a tree ring-like structure. So everything has a microstructure, and that microstructure is really important to understanding the material. And the data that we collect about microstructure as material scientists is image data, and we're really good at collecting it. We have many ways too. It's not just visual, it's not just optical signals. We collect electron-based signals in electron microscopy. We collect X-ray based signals, as well as optical signals in various modalities. We're very good at preparing and imaging the microstructures of materials. And so we have this data, and as you can see by this collage I've made at the bottom of the slide, it's incredibly diverse. These are materials ranging from the mayonnaise and hailstones that you've seen to nanomaterials, cast iron, ceramic materials, and so on. And you see there's just a lot of diversity in the patterns that are formed. In these patterns, material scientists see the structure of the material, that is what it is. For instance, I can look at this, but I don't know if you see my let me see, can I get my laser pointer up here? There we go. This structure right here, that's cast iron with those spidery graphite nodules. And I know that. I look at that and I say, oh, cast iron over there. If we also see the processing, how is the material made? Down here, I see what's called a dendritic structure. So I know this material was cast from the liquid state. And we see the properties, how will it perform? Up here, I see a superalloy, a nickel-based superalloy with gamma-gamma prime cuboidal particles in it, and I know it's very strong. And so there's a lot of information in this image data. So how are we going to extract it? Well, that's the goal of computer vision, of course. We would like to apply the tools of computer vision to do for our field, material science, what has been done in medical imaging, radiology, and so on. We'd like to use these powerful information extraction methods to get more knowledge out of our image data. All right, so now you understand microstructure and what we want to do with it. Let's talk about the issues that microstructure brings us. And the fundamental one is this: our data sets aren't big. These are costly data to acquire. They require experts to prepare the samples and to image the samples. And it's generally true that it's an extraordinarily large data set that has 1,000 images in it in material science. And so we have to turn to methods that allow us to deal with smaller data sets. Transfer learning is the main one. That is, we start out with a trained convolutional neural net. We might, in this particular case, I show you VGG16 trained on ImageNet. That's one of our workhorses in these workflows I'm going to show you. And then we, of course, use the learned parameters from the pre-trained neural net to create our image representations. And then we only have to retrain the final machine learning layers, the classifiers or whatever. I say that occasionally we initialize with the pre-trained neural net and retrain the whole network. That's also an option. But either way, we're going to start with natural image, with a CNN trained on natural images, and attempt to apply it to our smaller data sets of microstructural images. It works remarkably well, as you'll see, but there are issues in the fact that we are dealing with different kinds of images. So here's a few computer vision applications in microstructural science, and I don't expect this to be an exhaustive list either, but you'll notice it's very similar to the list that I showed you earlier as general computer vision tasks. We care about visual similarity. We care about classifying images according to their categories, object detection, especially looking for defects and anomalies, semantic segmentation and instance segmentation. We care about generating instances of images, as I'll show you later. Super resolution is a big topic in microstructural science right now. Prediction, especially prediction of properties from a microstructure. I'll show you an example of that. Optimization of microstructure, simulation surrogates, and the list goes on. So almost anything you can think of to do with computer vision is relevant to microstructural science. Here's one example, the simplest example. This is visual similarity. As Arti said, this is the Google search for microstructural images. Here, we simply use a pre-trained CNN, and we create it, and we use one of its layers, maybe the first fully connected layer, for example, to create a feature vector for each microstructural image in a database. And that allows us to compute visual similarity by comparing feature vectors, and that translates naturally to a visual search engine. And if you want to go to this link, you will see a very rudimentary web page with a visual search engine for a microstructural database. The beauty here, though, is that material scientists have traditionally described images qualitatively, and that makes it very difficult to do a search on these images because everyone uses different words. And so if I do manage to get a few thousand microstructures together, it's very hard to sort through them, to look through them, to search them, to ask, have I seen an image that looks like this image? With using a simple visual search, we can do that. And so that's actually a very valuable outcome for a rather simple computer vision task. Here's another one, classification. So we know the feature vector can be used to classify images based on their visual content. That's the classical neural CNN application. Here's an example where we take a database of, these are TEM images, transmission electron microscopy images of particulates. These are potentially toxic airborne particulates. They contain carbon nanotube particles. So they're sharp to your lungs. You don't want to breathe them. And NIOSH, the same organization that certifies our N95 masks, well, they're the government organization that cares about airborne particulates, including viruses. And we worked with them on this classification problem. They collect thousands of these images, and until we made a classifier for them, a human had to go through each one and classify it according to its toxicity. And I will say we didn't achieve the highest degrees of classification accuracy, about 91%, but that was more than sufficient to truly speed up the process that NIOSH needed to go through. So this was a benefit of, again, a simple computer vision task. We can go deeper with classification. We can start to understand science. And this is where interpreting the results of machine learning and computer vision become essential. This is a task where we have an aerospace alloy. It's one of the ones used in an airplane that you might, a commercial airliner that you might fly on. Titanium, 6 aluminum, 4 vanadium is the alloy, Ti64 we call it. And we were looking at forged material. That means we took a round billet and smashed it till it was flat. And we cut pieces out of that flat plate of titanium, and we broke them. And we looked at the fracture surfaces. And there were two different directions of crack that we looked at, called transverse and rolling, and TDRD. And we have a database of fracture surface images labeled with this binary classification, either transverse or rolling. The question we had was, well, can we look at those fracture surfaces and classify them? And indeed, we can get good classification accuracy. That's not too much of a surprise. But what was interesting to us was we did some cropping of the images. These were high resolution images. And so we said, well, we could actually crop them into sub images and have more training images for our system. And we did that. So no crop on the left is the raw image as we were given to them. Of course, we have to shrink them to the 224 by 224 size, pixel size that we use in the VGG16 encoder. But anyways, they're the full resolution image. Then we sliced the original image into 4 sub-images, and we improved the classification accuracy. And then we sliced again into 24 images, and we decreased the classification accuracy, and that decrease continued as we further sliced the original image. So that tells us something about what's important in these microstructures. It gives us a length scale. It says if you crop these images smaller than a certain size, we lose something important to the classification accuracy. We lose some feature that we need in order to get the best accuracy. So even though we're getting more training images, we're losing overall accuracy on the classification problem. And in fact, we can do filter activations to highlight what are the important features that are being tuned in upon by the machine learning algorithm. And that gives us an idea, first of all, of what those important features are. In this case, it's deep valleys in the fracture surface. And second, it gives us an idea of the length scale, which in this case is on the order of 40 microns or less, or slightly less. And so we have learned something about what we need to do to best image these and understand them. That is, we care about the valleys. They are important to the fracture mode of the material. That's telling us something about physics. And they have a length scale of around 40 microns, which we may need to make sure to capture in any data collection that we make on these materials. So interpreting what the model is doing is important to us. We can go further. We can go beyond classification to regression and start to predict things like materials properties. Here again, we have a rather small data set. This is high strength steels, and we have about 100 images of 7 different kinds of high strength steel, and we have metadata on their strength. How strong are they? We have excellent image quality. These are beautiful micrographs, but it's a small data set, only 16 images per alloy, and there's very subtle differences between the classes here. Furthermore, the metadata is low in contrast. In other words, 4 of the alloys have almost identical strengths, and the other 3 aren't too far away either. So this is going to be a low resolution, low contrast regression that we have to do. But we have hope. We can do unsupervised learning, that is just clustering. In this case, a simple TS&E clustering on our micrographs, again, by representing them with their feature vector from a pre-trained neural network. And we can see visual clustering, and that visual clustering does group according to yield strength. And so we have some hope that we can perform the regression task. I will say it was very difficult. One of the things we've learned is that regression is far more finicky than classification of any kind. And at the end of the day, my student Nangao was able to get a very good regression result. This is the prediction error on the y-axis. We want it near 0, and you can see for the different yield strengths that we have represented in our set of data that we're falling vastly. I thought I had the number here. Something like 90% of our predictions are within plus or minus 20 megapascals, which is very good accuracy for this prediction. But it wasn't without great travail. So regression we've found to be much more temperamental and much more dependent upon exact choices of parameters. So nonetheless, this is now a useful tool. We can actually look at a microstructure and predict what its property is, predict what its strength is. And this is very important in alloy design. I also have to put in a generative method. Who doesn't enjoy GANs these days? It's such a neat toy to play with, if nothing else. And we actually have uses for generative methods for microstructure. I show an example here in collaboration with my colleague Paul Salvador at CMU, and this is solid oxide fuel cell materials. These are the electrodes used in fuel cells, so very important to the hydrogen economy. Professor Salvador has a lot of very expensive, very impressive 3-dimensional pictures of these materials, 3-dimensional microstructures taken from experiments. So what we wanted to do, because this is such expensive images, such expensive images to obtain, we wanted to see if we could do a generative method to supplement that data set. And so we trained a GAN, a generative adversarial network, to generate synthetic 3-dimensional microstructures of these materials. They're complex 3-phase materials, and see if we could come up with this supplementation of experiments. I won't go into detail here. You're getting a survey. My hope is to engender discussion, but I will say on the left here are some real and some synthetic microstructures, 3-dimensional microstructures from the GAN. I'll let you look at them and decide which is which, but my material science colleagues were not successful in passing this test. The fake images, that is the synthetic images, are on the left and the real are on the right. We could actually measure many things about these structures, including their geometry and topology, and show that the synthetic and real structures are extremely similar in their, not only in their average values, but in their distributions. And the most important thing is this graph on the right. I don't expect you to read or understand it, except to say this. The blue symbols are the GAN microstructures. The open circles are the experimental microstructures called original. And what this graph is showing is the properties of those structures, and you can see that the GAN, the generated microstructures, and the experimental microstructures overlap beautifully, which means that we're not only creating structures that look right, they actually have the right properties, the right behavior as a material. If they were mayonnaise, they would spread correctly. And so that's a really beautiful result. We use these, by the way, for computational surveys of material properties. They help us design materials. All right, I want to finish up with one of the fundamental tasks that material scientists have always done, which is image segmentation. That is, we always want to measure things about images. And to do that, you have to identify those things, that is, segment them from in the image. And so we might start with an original image like that on the left. We have the graduate students sit down with a stylus and a tablet and outline the region of interest here, the lath-type bainite shown in blue. And we can train, of course, a CNN-based segmentation system to do, in this case, semantic segmentation, and we get excellent results. Now, this is a very low contrast segmentation. In fact, it's so difficult that the graduate student needs to actually use 2 imaging modalities in order to get it right. And the CNN is able to do this very, very nicely. Here's an instant segmentation example. We have particles imaged here. These are powder particles used in additive manufacturing, that is 3D printing. We want to, the graduate student, to identify each particle has to outline them with stylus. So we trained an instant segmentation system in order to do that object identification and instant segmentation task with great fidelity, and the results are very useful to analyzing these materials for particle size distribution, agglomeration, and satellites. We also do multi-component, again, semantic segmentation. On the left here is a high-strength steel or a high-carbon steel with multiple different components involved in its microstructure. The graduate student has to identify all of those, as you can see in the color scheme. And again, the CNN does a good job of segmenting. I show these here in part to show you the range of segmentations we might want to do, but I also wanted to make a point. For the low contrast segmentation, that was a very difficult job for humans to do. We trained the system I showed you with just 4 training images, 4 annotated training images. In instant segmentation, 4 training images. In multi-component segmentation, 1 training image gave us the results that I'm showing you here for the segmentation of the test images. And so we have some hope to take what is for us one of the most tedious, time-consuming parts of our image analysis pipeline. And with a very small investment in training data, that is in developing a ground truth set, we can get excellent results that we can use over and over again for the same materials. Why? Well, I think there's a basic reality about microstructural images. For natural images, you tend to have one instance of the object, in this case, my cat. You have to have various length scales. There's arbitrary fields of view. It is almost always oriented by gravity, but the outcome is that you need many images of my cat in order to capture all the visual features that you need to identify my cat in an arbitrary image. For microstructural images, they're data rich by intent. We are trying to take a picture that contains as much information as possible. And so we include many instances of the objects of interest. We try to capture the correct length scale to view the information. We use standard fields of view, often not oriented, sometimes oriented images. But this means we have information-rich images and we don't need as many of them to capture the full range of visual features that we need to do machine learning tasks efficiently with efficient training. Here's data frugal segmentation explained. This is again on the ultra high carbon steel database that we have. We have 24 manually annotated images in this database. So what we're going to do is we're going to train on 1 image and test on the remaining 23. And what we find is that we are able, if we choose a good image, as I'll show you in a minute, to come up with what would be, what would be excellent predictions and excellent IOU with only 1 training image. So, and I will mention, by the way, there's a minority component here, this orange component, what we call the Wiedmann-Sementite. There's very little of it in any individual image, and it's needle shaped. It's hard to identify, and it is definitely what drags the IOU, the intersection over union score for this segmentation downwards for all the attempts we've made. But that's okay. We still get it pretty good enough, certainly, to be useful for the materials scientist. So what's interesting is, again, interpreting how the models are working is vital. So we ask, okay, we train on one image, test on the remaining. Do different images give different results? Different training images give different results, and obviously they do. And we can look at, for all 24 of our training images, we can look at the IOU that was gotten for the segmentation. And what we find out is that, for instance, if we look at the worst case, that gave the worst intersection over union score, here's the image that was used as the training image. It's a poor choice because it doesn't contain all the constituents of the other images. It's only got 2 of them. It's got the ferrite and the spheroidite, specifically 2 of the 4 constituents. So unsurprisingly, it's not very good for training a computer vision system. Here's a better one. It got a pretty good IOU, and it does contain all of the constituents that we care about segmenting, all 4 constituents, including a little bit of Biedmann-Statten. It did better, but it's a different magnification than most of the images. So it's not ideal. The best image is image number 3 over here, and it has all the constituents represented. It's at the standard magnification. And what's really interesting to material scientists is it includes all the constituents, and it also includes these black dots. Those are polishing artifacts. Those are bad. Those are what we try not to put in our images because they're just artifacts. But the computer vision system needs those. It needs to know what to ignore as well as what to pay attention to. And so the best image for a computer vision pipeline may not be the best image according to a material scientist who cares about the constituents and would rather have no polishing artifacts. So that was interesting. We can quantify it. So a good image is representative of what we want to view and what we want to ignore. But we can quantify it. We can interpret this directly. We can ask, is the most representative image the one that is the best training image? Are the features in the image representative of the features in the other images that have to be segmented? So we can actually use computer vision pipeline to construct a feature vector. In this case, we're going to do it as it were with specific features. We're going to extract pixel level features, specifically hypercolumn features. We're going to cluster those features and then perform a bag of visual words. We're going to VLAD encode that, and that's a feature vector. If you want more detail, we can talk about it. But the main thing to say is we created a feature vector representing each of the images in our data set. And this is actually a very fast encoding. And then we define a representativeness metric based on the cosine similarity. We say if there's 2 images, we have their feature vectors. We compare the cosine similarity of those 2 images, and that is related to how representative the first image is of the second image, how similar they are. So higher similarity in images would correspond to a higher value of the representativeness metric. So then we go back to the results I showed you. These are the IOUs for the different training images, and these are the representativeness metrics. And we can see for high representative metrics, images 2 and 7 here, they're the 2 best training images that we had. We have high MOUs as well, MIOUs, mean IOUs. In other words, representativeness seems to be a worthwhile metric for understanding how good an image is as a training image. If we go to a moderate representativeness, this image here, number 8, we have a moderate IOU for the outcome. And likewise, if we look at the lowest representativeness, that's again that image that has only 2 of the 4 constituents and gives a very low IOU score for the segmentation. And so now we can, understanding what the system is looking at helps us define a representativeness metric that helps us determine which images are worth the difficult task of manually annotating in order to turn them into training images for the computer vision system. Saves us a lot of time. So my basic conclusions are this. Computer vision helps us do 2 things that are vital to microstructural science. Maximize the information extracted from our image data while minimizing the cost of doing so. And I'll leave it at that. I will thank all my group members, including the alums of the group, all the collaborators, I'm a computational materials scientist, so these folks on the right are the people who actually took those pictures, and I would love to answer any questions.